Assalamu alaikum wa rahmatullahi wa barakatuhu. Rabbi yassir wa la tu'assir wa tammim bil khair. So in this video we will continue with our topic of induction motor. So today we will in this video we will continue with this torque speed characteristics of the induction motor, which are very important aspect of the induction motor to understand, and that actually explains us how this motor actually works in the stable region or unstable region, or where it is operating in the system. So as we have seen this previously, that the angle between the B net and BS actually gives us the torque, and here we can see that if this load is very small, so we can see that this angle is very small. But if we have B net and BR, so but if we have this heavy loads, so this angle becomes large and will produce a large amount of torque for the requirement of the load. So we can actually see different parameters of the induction motor and to understand this torque speed characteristics. So the first one that we want to see is, as we know, that torque induced is K times PR B net sine delta. So first of all, we look at the BR, rotor magnetic field, that is actually which is plotted against the synchronous speed speed of the motor, and the BR, or the rotor current, because they are proportional. So we can have seen, so as we can understand from this graph, actually when the speed is 0 and the slip is 1, so at that moment we know that the huge amount of currents will flow into the rotor, as we have seen in the previous video, that the air gap power at that point will be equal to the rotor copper losses. So all the power that's been transformed from air gap will be consumed inside the rotor. But as the speed of the rotor is increased, as the speed starts rotating, we can see that close to the when the slip is say 0, so we can see that there is no rotor current flowing into the rotor. So obviously this is a portion which where we usually operate for the induction motor, and that's why we have this what you can see is this small amount of current that are flowing into the rotor all the times during the standard operation of induction motor, or when they are operating at the rated loads. Similarly, we can see the B net versus the speed of induction motor. So we can see that the net magnetic field stays constant for all the speeds, so it will not vary, because this is just the vector manipulation of this these two magnetic fields which are present in the induction motor. Now let's look at another important aspect, that's the torque induced. We know that this is equal to KBR B net sine delta, and angle delta is just equal to the power factor angle of the rotor plus 90 degrees. So delta is equal to theta r plus 90 degree. So here we can manipulate it as sine delta is equal to sine theta r plus 90, which is equal to cos theta r, and cos theta r is the power factor of the rotor. So cos theta can be written as tangent inverse xr over rr, which is equal to tangent inverse of s xr0 over rr. So power factor of the rotor will be then cos theta r, and that can be manipulated here. Here we can see that it obviously it never goes to 0, but it has some value at the start when the machine is in the halt position, or it is in the it's not rotating at all. We have just applied the power to the stator. But as we can see that as the speed of the induction motor increases, the rotor power factor tries to catch up, and it reaches approximately 1 at the synchronous speed. So here we can add them together, and we can divide this torque speed characteristics into actually three regions. One is called the slow slip region, low slip region, and then we have the medium slip region and the high slip regions. So the low slip region, obviously we know that slip is 1 here and 0 here. So low slip region will be these portions. So we will be approximately looking here. If you could here we can be approximately here at this portion, close to the synchronous speed. We will be here close to the synchronous speed. So when we are close to the synchronous speed, we can see that the IR is very small, B net obviously is constant. The rotor power factor angle is approximately 1, and the torque induced will be this one at this point. So obviously this we are, when we are close to the synchronous speed, means that we have some slip value, and that slip will define how much we are away from the synchronous speed. Okay, so this is called the low slip region, and most of the time this region is known as the stable region of the induction motor, and this is mostly the operating region of the induction motor for the rated loads and rated torques. Then the moderate slip region is here somewhere in this portion. But here we can see that in this region all the rotor currents are increased. B net is obviously the same. Theta will be less than 1 at some point. But here we can see an important aspect of this torque induced, which is known as the maximum torque that can be produced by the motor, and we call it as the pull-out torque. Now this pull-out torque means that if we add more load to the induction motor, it will not tolerate that load, and it may stop, like this. And obviously the motor has the capability to produce a certain amount of torque. Beyond that point, it cannot produce any torque. And also remember that the motor will only generate the torque which is equal to the load torque. Means how much load we have put on the motor, that will decide that the torque, how the motor will produce the torque. So that's why here if we have this peak torque, or we call it as the pull-out torque, sometimes we call it as the peak torque. So pull-out torque means that the maximum torque that can be added to the motor so that it can operate for means obviously we cannot put this load for longer times because it is not good, because we have the high rotor currents and the cos theta r is less than 1. Sorry, cos theta r is less than 1, and we have the maximum torque then. And this is pull-out torque. This is actually the moderate slip region. So we have 0, and it would be somewhere here at maybe 0.2, say maybe 0.6 or 0.7. You cannot define it physically exactly, but it totally depends upon these curves, actually depends upon the different motors. They have the different characteristics, but the basic shape will be the same. Then we have the high slip regions. These high slip regions are the starting points. Remember that we cannot operate the motor at these points over a long period of time, because this is a starting point. So if you say that this is the torque which is produced at the starting, that's why induction motors can be started with the load in the industries. So sometimes it's better if you offload the motor and then add the load after starting it, but still if you have not the capability to remove the load at the starting point, so we can start the induction motors initially with the load, and this current and this load is actually around 100 to 200 to 300 times the rated torque. But still, this is actually the high slip regions are the starting part of the motor. Obviously this is not the stable region. We have to increase the speed. Still we reach the desired speed at the desired load. So I hope you have understood this torque speed characteristics of the induction motor. This is very basic phenomena that you must understand to understand the behavior of the induction motor at different operating points. So that will actually helps us to understand how the motor is behaving, and why how differently behaving the motors at different operating points. What's happening inside the motor, how the torque is produced, and how much torque it is producing at different slips. So still, if you have any questions, please feel free to ask. Stay blessed. Assalamu alaikum wa rahmatullahi wa